let's start with the demonstration. I set up a couple of virtual machines on my PC. On one hand, an OpenBSD machine that I use as validator. I've chosen OpenBSD because I'm very familiar with it, and it ships with almost all the needed software that I needed for this lab already pre-installed. Only this RPKI RTR protocol implementation I needed to install from a package. The rest is all ships in base. Then I have a Juniper router, a virtual one, and an Arista box, a virtual one. And I show you all the components and how to configure and check the status of them. So I need my console. So these software stacks, some of them support RPKI since a long time, namely Junos. In version 12.2, I'm not sure when it was published, but quite a couple of years ago, it had support for RPKI. EOS from Arista started supporting it last spring. And OpenBSD with the version 6.7 shipped with an enabled RPKI client. This is the validator software. And this was shipping spring last year. So let us check what we have on the validator. Again, the picture. We have an RPKI client. And the RPKI client, actually, it's not a daemon. It's a program that you can run manually or by cron. Here it's commented out because I did run it manually. So you just run RPKI client. It then uses all these tall files. We see in this directory, we have 5 tall files. And if we check the one from RIPE, we see the URL where to fetch the information and then the signature. It then fetches all this information and validates it. It stores the data it fetches, it retrieves from all these repositories in a cache. And here we see that it actually fetches data from more than from these 5 internet registries, but also from a couple of delegated certificate authorities. And in there, we would find all these objects that we can inspect through console rpkiclients.org that we checked before. It's just not as readable if you do it here compared to the website. Once it has checked all the signatures, it outputs the information without all the certificates in it. You can choose the format here. The default format is one that can be used by OpenBGPD, and for most other tools, they can use a JSON file that is emitted by this program. Let's have a look at this one. So we have some metadata and then all the ROAs. And we see how this looks like. For every prefix, there is a line here or an object which has the AS number, the prefix, the max length, and from where it has the information. So what else do we have on this box? To actually show what a router is doing with it, I need another BGP speaker which sends some prefixes, some valid, some not valid. And for this, I use the BGP daemon on this validator, which of course in production makes no sense, but for demonstration purposes, it's okay. So you see here we have two BGP sessions, one to our virtual MX router, one to our virtual EOS router. And we can also see what I'm announcing. So the last prefix would be legitimate. The others two would not, according to who the prefix actually belongs to. And here in this output, you don't see my AS number. Here in the config file, we can see the AS number 6830, and again, the three networks I'm announcing. So now let's check how it looks on the routers, just to see that everything is set up. So this is our virtual Junos device. We see session is up, established. We receive and accept three prefixes. And we can also look at them into detail. Yes, we receive all three prefixes from our other router. Now we should see the same on our EOS device. As expected, one BGP session is up, is established, and we received three prefixes. And here we see the routes that we received. Okay, all good. Right now, RPKI is not active yet, or actually what is not active is if we switch back to the picture. I did not start this Go RTR software. So we have all the validated ROAS in the cache. We have seen that this OpenBGPD announces the three prefixes to the Juniper and the Arista box, but they cannot yet validate because Go RTR is not running. But I wanted to show you that now they accept all three prefixes. Now let's start this service. So it has now checked this JSON file. And in a few seconds, the two routers should connect. Then we should see that a connection pops up here. Yep, they're both here now. The 12 is the Arista box and the 11 is the Juniper box. Okay, now let's see if something changed. And we see now we only have two routes on the Juniper box. And we have some additional information. Before, You've seen validate state unknown. Now we see with one prefix, validation state valid. With the 888 prefix, we see validation state unknown, which means that for this prefix, there is no information in the RPKI system. But the third one disappeared. Actually, we have a hint here. It's hidden. So let's look at this one, the 111. And here we have the reason validation state invalid. So actually this prefix was now not accepted because according to the RPKI information, it is invalid. Now let us check some more details. Actually, let's look into the configuration. The connection to this GoRTR software first needs to be configured. Of course, I already configured it, otherwise we would not have seen the effect. In the routing options stanza from Junos, we have well, I wanted to say new, but it's actually in Junos, it's not new anymore, the validation. And there we can define multiple sessions. Of course, in a production environment, you want to have more than one session. You want to have more than one cache and sessions to all of them. But this is how you specify that the Juniper router should actually communicate with our cache and fetch information from there. We can then on the router also see what is in there, what is our validated data. I stop here, but you can see we have all the information that we've seen was previous in this JSON file. We also have it in this database. We also can check if the session to this cache is up and running, and it looks good. Here we also see how many entries we have there. There's also some statistics. I find this interesting because it shows how much memory is needed for all these entries. We see we need now around 40 megabytes of RAM for all this data. It's not nothing, but also not that much. But if the adoption of RPKI increases, of course, memory consumption will also increase. So with this validation configuration, we tell Junos to actually connect to our GoRTR service and fetch all the information. And actually it also pulls this and will update and will get updates. But now we need to connect this information with our BGP process so that it acts on it. And this we do with policy options. And I called the policy route validation. So that's my name that I've chosen. So we have multiple terms. It checks if it's from protocol BGP, and according to the validation database, it is valid. Then we mark it as valid and accept. Or you could also formulate that you then continue processing other policies. If it's invalid, if the validation database says this entry is invalid, then we mark it as invalid and reject the route. And then there's also unknown. This is if there's no information about this prefix or about this route in the RPKI system, then of course it's unknown and there's no reason to reject that. Or not yet. Actually, in Junos, there's a fourth state, because I might have some BGP sessions where I do validate, but there might be other sessions where I don't. So there is a fourth state not validated, so that I can also act on that if I want to change priority, for example. And the last step then is to connect this policy with my BGP configuration. You see, for this setup, for this demo setup, it's quite a simple configuration, and I only have one import policy. That's the policy we looked at. And that's how it works on Junos. Now let's look into Arista. On one hand, before we've seen that we receive 3 routes, the assumption is that now we should only see 2 of them, because one is invalid according to RPKI. Oh, that was the wrong command. But our session is still established. But actually, we see here we received 3 prefixes and accepted 2 of those. And voila, the 1111 prefix is gone. Actually, we also get some more details. If you see what we actually received from the neighbor, and here we see clearly that the route that is now not accepted has an I here, which means according to RPKI origin validation, it's invalid. And the 888 is unknown, like on the other box, but this one is a valid prefix according to RPKI. Let's look at the configuration. So first, to make use of RPKI on Arista, you need to switch to the multi-agent model. If you use the other mode, or the default mode for the routing protocols, you don't have an RPKI support. And if you do that, you also need to reload your box. And then we already see we have some route maps. And also, I made it quite simple. We have first a deny statement, and if it matches, if the prefix matches and the validity is invalid according to RPKI, then we deny, we reject, and otherwise we accept, or actually here your regular policies would follow. And with this statement, we activate the route map for this particular neighbor. And in the router BGP hierarchy, we configure our session to our validated cache. We specify the IP address and the port of the validator. I specified some intervals. Well, actually, I lowered them. Otherwise, I think it's okay to just leave them at default. I lowered them. So if I play around in the lab, I see the effects faster. And that's also a good point, transport TCP. Currently, that's the only thing you can choose, but the RFCs actually say that you, or define multiple ways to secure this connection, because this connection is not secured. The assumption is that's in your network, and there you can take care that it's secure, but actually the RFC recommends that you secure it, be it with IPsec, you can, or be it with, it does specifies the use of SSH for this, or TLS, or even though it's deprecated, TCP MD5, or the successor of it, TCP AO. But many implementations only support, on the routers, only support plain TCP. I guess this will change over time. And then with the last statement here, we define that for eBGP sessions, we want to use the locally available database to do the validation of the prefixes. And of course, also on Arista, we can see what is in our cache. So actually, that's the session we have, and the connection is active. And now we can also look into the database. So that's the summary, which only shows us how many entries we have per address family, and through which cache or session we get how many entries. And of course, we can also look into all the content. Now, if you run that in production, the question is, of course, what is the risk if something goes wrong with my validated cache? So if it still delivers stale data, then of course your router validates according, or validates or checks against old data. Because of that, you probably should check that your validator software is running. In the case of RPKI client, you can check the logs that it's actually triggered by the cron daemon and that the file changed. And there are some other things you can check, but what you also want to know, what happens to the system if it stops working? So if I just stop it. So the router's now lost the session to the validated cache. What happens? So it takes a little bit, but in the end, all the entries, we will accept again all entries, and they will all be marked as unknown. Because in the configuration, I specified what is the timeout, and if the local cache cannot be updated, how long should it wait, and when should it remove all the stale data? Okay, now it takes longer than, now here it is. So now we see all the entries are now unknown. On the Arista side, I cannot show you that yet because the minimum there is, if I remember correctly, 10 minutes. So we would need to wait 10 minutes to see the same effect. Of course, if you would have a session to a second cache, then you would still have valid data. Yeah, but what I wanted to show you here is that if the RPKI infrastructure does not work, you kind of fail open, which in this particular situation is okay. Whereas in other areas in IT security, it's definitely not what you want, but here it's okay. Okay, so I hope I could show you that it's not too hard to actually set it up. Of course, in a simple lab, it's easier and less things to look at than in a production setup. But still, I think with these implementations, I could show you that it's not rocket science anymore.